So today we are going to learn about the deviations from the Beer-Lambert law. Before learning the deviations, let's have a quick recap of what we had learned in the Beer-Lambert law in our previous video. So here we have a polychromatic radiation which is being emitted from the source of light. This polychromatic radiation consists of all the wavelengths included in it. So this is passed through matter, which is actually a dispersive element and is continuously rotating. So the rotation of dispersive element actually splits the polychromatic radiation into different wavelengths, and that is why it is called as a monochromator. Monochromators generally have a diffraction grating to disperse the radiation into its component wavelengths. So that means now we are having the radiation with different wavelengths, as you can see, which are being depicted with the help of different colors. And through the exit slit, the monochromatic light passes out and strikes our sample, which is actually a homogeneous mixture of the solute in the solvent. Now what happens, basically every molecule in this sample is capable of absorbing its own characteristic frequencies of electromagnetic radiation. So during this process, the energy transference takes place from the radiation to the molecule, and this results in the decrease in intensity of the incident radiation after it is passing through the sample. So we get the transmitted light with a decreased intensity of radiation, which actually then strikes the detector. And hence we got the Beer-Lambert's law, which states that A is equal to epsilon times X times C, where A is the absorbance of light, epsilon is the absorptivity, X is the path length, that means the length of the path which the radiation has traveled inside the sample, and C is the concentration of the sample. So the absorption law, which is also known as the Beer-Lambert law or just Beer's law, also is sufficient. It tells us the quantitatively how the amount of decrease in intensity depends on the concentration of the absorbing molecules and the path length over which the absorption occurs. So by this we can say that by varying the path length and the concentration, the validity of the Beer-Lambert law can be tested and the value of epsilon may be evaluated. Molar absorptivity depends on the wavelength of incident light. Remember, molar absorptivity term is used when the concentration is taken in terms of molarity. So molar absorptivity basically depends on the wavelength of incident light, the temperature and the solvent which is being used. So we get this type of calibration curve for the Beer-Lambert law, where you can see that this calibration curve, or the blue line which is being seen over here, passes through the zero and is actually a straight line passing from the zero. So this calibration curve or the line may be used to determine the unknown concentration of the solutions of the same material after the measurement of the absorbance. So we can say that typically Beer's law holds over a wide range of concentration if the structure of the colored ion or the colored non-electrolyte in the dissolved state does not change with concentration. But remember, the straight line is obtained only when the absorbance is plotted against the concentration. However, if we plot transmitted light intensity or the transmittance with respect to the concentration, we get a curve like this. So discrepancies are usually found when the colored solute ionizes. That experiment does not follow the Beer's law. When the experiment or when your sample is not following the Beer's law, we call it as the deviation from the Beer's law or the discrepancies. So these kind of discrepancies are found when the colored solute ionizes, or it dissociates or associates, leading to the association of two or more molecules in the solution, because the nature of the species in the solution with concentration, it changes. So in those cases, the law does not hold when the colored solute forms complexes, the composition of which depends on its concentration. Now we see that the transmittance and absorbance cannot be measured as such having a solution in a container. So we need to take the solution in a proper container, which is called as the sample holder, and technically it is called as a cell or a cuvette over here in UV visible spectroscopy. Cuvettes are made up of quartz, or it can be made up of glass also, and nowadays some polymer based cuvettes are also used. So when we use the glass as the material for the cuvette, or in other words, when we use the glass cuvette, there ought to be some reflection and scattering of light also, and these reflection and scattering losses can occur at the cell walls or the wall of the cuvette. Now these losses can be substantial enough, like you see an incident beam is striking the sample having a high intensity, and it is transmitted with decreased intensity of the light. So we were talking about the scattering of light, we were talking about the reflection and the interference losses, which can be substantial. For example, it is known that 8.5% of a beam of yellow light usually gets lost by reflection when it passes through the cuvette, when it passes through the glass cuvette. A light can also be scattered in all the directions, like here. Scattering of light is taking place from the surface of large molecules or particles, such as dust particles or any other molecule present in the solvent, and this scattering can cause further decrease in intensity of the transmitted light as it passes through the solution. Now these kind of deviations, these kind of phenomena which are taking place inside the sample, inside the cuvette, inside the sample holder, in fact they also need to be considered. So to compensate for these effects, the power of the beam transmitted through a cell containing the analyte solution is compared with that traveling an identical cell containing only the solvent, or we technically call it as a reagent blank. So an experimental absorbance that closely approximate the true absorbance for the solution is obtained in that case. This straight line will not be obtained when you measure the absorbance of the different concentration of your solution you have prepared, and when such phenomena happens, we call it as a deviation from the law, which can be due to different reasons, and you can have a negative deviation as well as a positive deviation also when your curve deviates from the straight line. Now there are different types of deviations from Beer's law, like it is mentioned, it can be a real limitation, it can be a chemical deviation or instrumental deviation. Now let's talk about these different kinds of deviations in detail. So starting with the real limitation, these actually are the fundamental deviations, because we know that Beer-Lambert describes the absorption behavior only and only for dilute solution. So it is a limiting law. That means that at concentration higher than usually 0.01 molar, the average distances, what happens basically when you increase the concentration to this particular beyond this particular limit, the average distance between the ions or the molecules of the absorbing species, that means your solution, they get diminished to the point, to an extent where each particle affects the charge distribution and thereby the extent of absorption of its neighbors. So every particle is actually interfering in the absorption process of its neighbors. Now since the extent of interaction depends on the concentration, so the occurrence of this phenomena causes a deviation from the linearity between the absorbance and the concentration. A similar kind of effect sometimes occurs in dilute solution of absorbers which contain high concentration of other species, especially the electrolytes when you use. So when the ions are very close to one another, the molar absorptivity of the analyte can be changed because of the electrostatic interactions which can lead to the deviation from Beer-Lambert law. So when the ions come closer together, when the distance is diminished between them, when the molecules come closer to them, actually the electrostatic force of attraction can come into play, and thereby deviating the data from the Beer-Lambert law. So basically Beer-Lambert law is applicable to low concentration. So the deviation, that is why the deviation is observed when the concentration exceeds this particular value. It arises from the change in the refractive index of the analytical system, of the system that you are studying. Why? Because at higher concentration the refractive index, it changes considerably, and when the refractive index changes, absorptivity also changes. The extent of interaction between the molecule decreases, and absorptivity is truly not constant and is independent of the concentration, as we have mentioned in our first slide, that the molar absorptivity, it basically depends on the wavelength of incident light and the temperature and the solvent which is being used. So it has nothing to do with the concentration of the solution or of the sample. So basically what we get from this slide is that the molar extinction coefficient, that is epsilon, it depends on the refractive index of the absorbing medium. And also if the initial concentration of the absorbing medium is greater than 0.01 molar, then what happens? The refractive index changes, and so epsilon also changes. On the other hand, if the concentration is less than 0.01 molar, the refractive index does not change with the concentration, and so epsilon does not changes, and in that case we say that the law holds true, or there is no deviation from the Beer's law. Next we come to the chemical deviation. Now what happens, as we know that from the real limitation, it basically depends upon the concentration. So our limitation is concentration of a sample over there. Chemical deviations actually occur when the absorbing species, they undergo association or dissociation, or rather any other reaction with the solvent to give rise to the products which actually absorb differently from the analyte. Means the product which is being formed after the reaction, they are giving absorption at some other wavelength as compared to the parent molecule. So the extent to which such deviation occurs, it can be predicted from the molar absorptivity of the absorbing species, and also the equilibrium constants for these equilibria. But unfortunately there is no opportunity for us to correct the measurement, because we are usually unaware of the fact that such processes are affecting the analyte. So the typical equilibria which give rise to chemical deviation of such kind include the monomer-dimer equilibria. It can be a metal complexation formation. So a metal complexation equilibria where more than one complex is present, or it can be an acid-base equilibria and the solvent-analyte association. So these kind of reactions can basically occur. For example, benzoyl alcohol in chloroform, it exists in polymeric form. So basically what is happening over here, association of molecules is taking place. So in this case also a deviation from the Beer's law will be observed in the graph, that is called as chemical deviation. You can consider another example of dichromate ions when they are diluted with water. Actually this dilution of dichromate ions in water is done at constant pH. So if we do the dilution of dichromate ions with water at constant pH, we get a straight line. That means the system obeys the Beer's law. But if the dilution is not done by keeping the pH at constant, then the orange colored dichromate ions actually they react with the water molecules to give chromate ions which are actually yellow in color. So the color of the solution changes. So in this case also we do not get the system which follows the Beer's law. You can also understand this system in another way, considering the equilibria wherein the chromate ions in acidic medium are there and they give rise to the dichromate ions and water. So the dichromate ion absorbs in the visible region at 450 nanometer. But when we dilute these dichromate ions, the equilibrium shifts to the left. That means more of the chromate ions will be there. The equilibrium can be controlled by converting all the chromium of the dichromate to the chromate by making the solution 0.05 molar in potassium hydroxide. Beer law will be followed in that case. So chromium should not be expected to follow the Beer's law in a highly acidic solution, because the dimerization step is dependent on the concentration even at constant pH. We can take another example of unbuffered solution of indicator, wherein you can see this particular graph is obtained. So the figure shows a chemical deviation from the Beer-Lambert law for an unbuffered solution of indicator, and at a wavelength of 430 nanometers, absorbance is mainly due to the ionized indicator, that is ion minus form of indicator, and that is actually proportional to the concentration of the fraction of the indicator ionized. So the fraction ionized varies non-linearly with concentration. This is what we can see from here. At lower total concentration, basically what happens, the total concentration will include the concentration of indicator and the concentration of the ion minus, that is the ionized indicator. At lower value of this total concentration, the fraction of indicator ionized is larger than at higher total concentration. So we have a positive deviation, or let's say an error occurs. At wavelength 570 nanometer, the absorbance is basically due to undissociated acid. The fraction in this form begins as a low amount and increases non-linearly with the total concentration, giving rise to a deviation. So we get a negative deviation and a positive deviation. The two deviations, they occur at 430 nanometer and 470 nanometers, which are basically happening. The deviation is basically happening because we did not use a buffer. We did not keep the pH as constant. So unbuffered solution of indicator can lead basically to the deviation from Beer's law. The next type of deviation is the instrumental deviation. Now, instrumental deviation actually is seen wherein the monochromatic radiation is not used. Why? Because basically Beer's law is applicable only when the monochromatic radiation is used. So if a polychromatic radiation is used instead of the monochromatic, then a beam of radiation consists of just two wavelengths, or rather three wavelengths. So we see a deviation in the Beer-Lambert law. And of course, we can see that the relation is not linear between the absorbance and the concentration when the molar absorptivities are different. So basically what happens when an absorbance measurement is done with the radiation which consists of more than one wavelength, that means a polychromatic radiation, then the power of the beam which is emerging from the solution or the sample is actually the sum of the powers of the emerging beams of the two particular wavelengths or three particular wavelengths, or those number of wavelengths which were used, which were present in the incident light. So in that case, the relationship between the absorbance and concentration no more remains a linear factor, and with that, when the molar absorptivities differ. In addition to this, the difference between the absorptivities between the two radiations, the deviation from the linearity increases, and when this situation is expanded to include more additional wavelengths, the effect will remain the same. So no matter you take two wavelengths, 3 or 4 or 5 wavelengths, the effect will remain the same. Now, if the band of wavelengths selected for the measurement corresponds to a region of the absorption spectrum in which the molar absorptivity of the analyte is, let's say, constant. So in that case, deviation from the Beer law will be minimal. Many molecular bands in the UV visible region of the spectrum, they fit into this kind of a description wherein the molar absorptivity is almost constant. Then we say the system follows the Beer's law effectively. But on the other hand, there are certain absorption bands in the UV visible region and many in the IR region also, which are narrow, and they deviate from the Beer's law, which is commonly observed. To avoid such deviations, it is best to select a wavelength band near the wavelength of maximum absorption, or the lambda max that we say. We also observe the deviation if the width of the slit is not proper, because in that case, if the width of the slit is not proper, then radiation falls on the detector, which is also absorbed by the impurities present in the sample, and that will actually change the absorbance of the sample. Of my results will be having an error. The graph which is mentioned over here actually shows the effect of different molar absorptivity, which we just mentioned. So we have three different curves. These curves actually are having different values for molar absorptivity, as you can also see. In one case, it is epsilon 1 and 2 as 1000, so the molar absorptivity is same. This is what we just mentioned, that if there is minimum difference in the molar absorptivity, or there is no difference in the molar absorptivity, you get a linear graph. Now, if the molar absorptivities are not same, then what happens? A deviation from the Beer's law takes place, which you can see in the orange and the gray color graph over here. In the orange colored curve that you get, the molar absorptivities are totally different, 1500 and 500, epsilon 1 and 2 respectively. So we are not supposed to get the Beer's law properly. The deviation from the Beer's law occurs. On the other hand, yes, of course, if we further change the molar absorptivities, then again a deviation will occur, and the extent of deviation will depend basically on the values of molar absorptivity, or the difference between them. This is what we are getting from the graph. So such kind of deviations actually are called as instrumental deviations, basically arising from the instrument as a reason. Maybe the use of polychromatic radiation instead of monochromatic, maybe because of the width of the slit is not properly defined, maybe because their molar absorptivities are different, maybe because of the cells or the cuvettes are not matched. That also is one of the reasons of getting instrumental errors. So in that case also, deviation from the Beer's law occurs if the cells or the cuvettes are not matched. The two cuvettes which you are using, one for the reference and the other for the sample, should be matched. So if the cells holding the analyte and the blank solutions are not of equal path length, what do I mean when I say they should be matched? Means they should be having equal path length. The value of x should be same for those. So for the cells which are having the analyte and the blank solutions, they do not have equal path length and equivalent in the optical characteristics, then definitely there will be a deviation from the Beer's law. An intercept will occur in the calibration curve, so the curve will not pass through the zero. In that case, this error can be avoided easily either by using carefully the matched cuvettes, or by matching them before doing the experiment, or by using a linear regression procedure also to calculate both the slope and intercept of the calibration curve. And in most of the cases, linear regression is the best strategy, because in that case an intercept can also occur if the blank solution does not totally compensate for interference. And these basically are the instrumental deviations. Also, if the photomultiplier tube which is used is faulty, it's having a fault, it is not properly working, then a straight line will be obtained for the absorbance versus concentration curve, but it will not pass through zero. Instead, it will cut at the concentration axis at any value which is not zero, other than zero. So this is also can lead to the instrumental deviation. The solutions which do not follow the Beer-Lambert law, it is best to prepare the calibration curve first using a series of standards of known concentration. And for more precise work, each calibration curve should cover the dilution range which is likely to be encountered or taken up in the actual comparison. Thank you for keeping in pace. Stay connected.